Last time we introduced the idea behind this class of understanding programming languages through their semantics and using that as a guide towards implementation. We made a language, J1, which I didn't mention but is based on this language called iSwim, which stands for if you see what I mean. And in the J1 language, we had expressions which were either values or they were function calls or they were if statements. And then values were constants, and then constants were either numbers, booleans, or primitives. And primitives included stuff like addition, subtraction, multiplication, division, comparison operations, and so on. All right. Now, we also talked about the idea of what's called a big step semantics, which is realized in a function called interp, which takes an expression and returns a value. The reason that this is called a big step semantics is because it takes you from the input program to the answer all at once. Now, there's two things, there's two things that are a little bit problematic with this. The first one is that once we introduced the delta function, which is partial, this big step interpreter now becomes partial as well. Because, for instance, what should this return if we call interp on dividing 1 by 0? Well, when we call the delta function on division 1 and 0, it returns bottom, meaning that it doesn't return at all. Therefore, this interpreter can't return at all. So this interp function is now partial. Since it's partial, that means that it can't tell us anything about what happens while this program is running. It only tells us what the answer is if there is an answer. But if there is no answer, then it doesn't say anything. So that's unfortunate. And that's not like math. Math doesn't work this way. It isn't like this. Instead, math has what's called an equational theory. For example, the equational theory for arithmetic says things like that a plus b is equal to b plus a, that 1 plus 1 is equal to 2. And so when we look at something like 2 plus 3, we know that that is the same as 2 plus 2 plus 1, which is the same as 4 plus 1, which is the same as 5. So we have this sequence of steps. We can, expand things. 3 goes to 2 plus 1. We can combine them. We can do all sorts of operations. Now, typically, when you do mathematics, when you do arithmetic when you're young, you do what's called a small step evaluation. For example, if I give the following problem to my my 9-year-old, I say, all right, can you add 1 plus 2 times 3 plus 6 times 10? And what they're going to do is they're going to say, aha, well, the first thing that I do is I turn this into 1 plus 6 times 10. Then I'm going to turn that into 1 plus 6 plus 60. Then I'm going to turn that into 7 plus 60. Then I'm going to turn that into 67, and that's the answer. So notice that this is not one giant step where we take the input program and we immediately go to 67. That is a big step. Instead, there are little tiny steps, and each step gets us closer to the answer. Right? And you know you've got the answer when there are no more steps to perform, or when you have a value. So you're done when you get v, i.e. a value, or there's no steps left. And it turns out that these are equivalent things. Well, they're not equivalent. If something is a v, then there are no more steps left, but sometimes there are no steps left and you still haven't got to a v, such as when something's partial. In other words, we can build a big step interpreter. We can write interp like this. We can say, let e prime be equal to step of e. And we say, if e is equal to e prime, then return e. Otherwise, it says otherwise, call interp on e prime. This big step interpreter is built out of a simpler small step interpreter that shows us each step, each intermediate step along the way. We can build a small step interpreter for our language, J1. Let's do it. So we have rules like the following. So we have a step function, and step takes an e and returns an e. And when you call step with if true et ef, then it returns et. If you call step with if false, really, if I want to be more precise, I should write this the following way. I should say v where v is not false. ETEF, then it is EF. If we call step on some primitive and we have some sequence of values, then this is equal to calling delta on P and that sequence of values. If we call step on a value, then we get back that value. So these 4 rules are the main rules that matter. However, we need to have a few more rules. So notice that in math, when we do this, we can do the 2 times 3, even though it is part of a larger expression that we haven't done yet. So we similarly would like to be able to do the same thing. We'd like to be able to evaluate inside of arguments. So how can we say that? Well, what we would do is we would write the following. We'd write down step of we'd write down step of if e that's not inside a value, etef, is equal to if of step e, etef. And so the idea here is that if we get an if where that position right there is not a value, then we can call step on the inside. If we call step and we have a sequence of values, and then we have one expression that's not a value, and then some more expressions, then that is equal to the same sequence of values, then we call step on E, and then we leave these args alone. Okay? Now, these rules, what they do is they allow us to simply define where the action happens. So these ones are called congruence rules, or structural rules. And these ones are evaluation rules. That says evaluation rules. Okay. It is so common to have congruence rules like this that what we often do is we create an abstraction of them that's called a context. A context is a way of indicating where evaluation can happen. The idea of a context is essentially to say, let's imagine a program with a hole in it somewhere. So imagine that I wrote down the following program. So hold on. So we have our evaluation rules, we have our congruence rules. What we'd like to be able to do is we'd like to factor out these congruent rules and have them be and have them specified in a separate way. We do that with a tool called a context. A context is a program with a hole. Okay. So what does this mean, a program with a hole? So we write down a context with the symbol C. And so we either have a hole or we have one of the different kinds of programs. So there can be if statements. Now the thing is that where can there be part of a if statement missing? Well, it could be in the first position. It could be in the second position. Or it could be in the third position. And then what about function calls? Well, a function call can have any number of expressions, and then a context, and then any number of other expressions. There's always at least one context somewhere. So for example, if I were to write down this program, by the way, normally when we write a hole like this, as a box, okay? So if I were to write down this program, plus 1 if plus 2 hole 3 4, okay? What kind of thing is this? Well, what it is, let's call this an AppC for an application context. This one will be an if 1C, an if 2C, and an if 3C. So what is this thing right here? Well, it is a hole, sorry, it is an AppC with a list of a plus and a 1, and then there's a hole, and that hole is an if 1C that has an AppC inside of it that has a plus, a 2, then the hole, then an empty list, because there's nothing after that, then there's a 3 and a 4, and then after that there's another empty list. Okay, so this right here, this program right here with that spot missing is this structure right here. So the idea is that a context describes a program where part of that program is missing. Now, why might this be interesting? Well, it's interesting because essentially what happens when you are talking about congruence rules is you're saying, let's leave everything the same about the program except one little part, and let's just vary that one part. Now, let's actually take a little bit of a a little bit of a sidetrack about this to really nail down exactly what we mean by this. So let's look at a simpler example. Suppose I have the program if equal 2, 2, 3, 4. Okay. This program right here, we can't run this first rule because the if does not have a value and it doesn't have false. Instead, we need to use this rule right here, this first congruence rule. What we could do is we could split this program up into two pieces. Piece number 1 is a program with a hole. And piece number 2 is the operation inside of the hole. This operation of splitting the program up, we call finding a regex. Regex here stands for reducible expression. Then what we could do is we could take the step function and run it on this piece and turn that into true. Then we could take these pieces back together and form them back up into a whole program that doesn't have a hole anymore. This operation is called plugging. We can write down the definition of the plug function very easily. Plug takes a context and an expression and returns an expression. When you call plug on a hole and an expression, you just get back that expression. When you call plug on an if1 C with a C, an ET, and an EF, and some expression, then you get back an if where you take that context, and by the way, sometimes we write plug in the following way. We write CE means the same thing as plug CE. Okay? If CE, ETEF, and if we have plug of an APC of the before, the C, and the after, where these are lists of things, then we would get the before, then we'd plug in the E, and then we'd have the after. Okay? So now the value of this is that we can specify our rules, our congruence rules, in a more convenient fashion. We can write them down like this. We can say that if you step on a V, you get back the V. If you step on if, false, ET, EF, you get back EF. If you step on if V not equal to false, ET, EF, and that's equal to ET. And if you step on P, V dot dot dot, you get delta P, V dot dot dot. And then we're just going to have one final rule that's going to say if step E equals E prime, then step CE equals CE prime. And so now we've factored out the definition of the context from the definition of the step function, and we can keep those two concepts separated. Okay. We can actually maybe simplify it a little bit more, actually, by just removing this and instead putting the C around these and saying that whenever inside of a context you have an if where you've reduced the pieces, and you can go inside there and replace it the following way. So that is a really convenient way to specify our semantics, because we only have to specify these 3 evaluation rules, and we can specify the congruence relation separately. Now, there's something not quite right about the rules that we've written down so far, but I want to take a little sidebar and talk about context for a moment. Contexts have this other interesting property, which they allow us to reason about when 2 programs are the same. So, simple little note. So when are 2 programs the same? Now, one meaning of them being the same could mean that they are literally exactly the same. For instance, 1 plus 1 would only be the same as the program 1 plus 1. But math isn't like that. Math doesn't say that that expressions have to literally be identical for them to mean the same thing. For example, a program that did 1 plus 1 is indistinguishable from another program that did 1 plus 2 minus 1. Although this program is written in a different way, it still has the ultimate same value. Now, you might say to yourself, yeah, but I like the one on the left better, because it's smaller, for instance. Well, in fact, this is exactly what compilers and optimizers do. You write a program like the one on the right, and what it does is it discovers another program that means the same thing that is more preferable in some metric. Maybe it runs faster, maybe it uses less memory, something like that. It certainly can be really convenient sometimes to write something like 2 minus 1, so you can remember that, aha, yes, it really is important that it's 1 less than whatever 2 is, right? So you don't have like multiple constants in your program. Well, we can express this idea that 2 programs are the same. 2 programs are the same as the following formula. We would say, for all contexts, the 2 programs being x and y, 2 programs x and y are the same if for all contexts, when we evaluate a context where we fill it with x, it's equal to the same thing as when we evaluate a context and fill it with y. This is essentially saying 2 programs do the same thing. If you can imagine any other program in the whole world that is missing one little piece. And on one side, we're going to fill it in with x. And the other side, we're going to fill it in with y. And after we fill it in with the 2 different things, if they still behave exactly the same, then the programs mean the same thing. This is a really, really powerful idea, and it's called observational. I just wrote obversational. It's observational equivalence. And it is a powerful principle for comparing programs. It basically establishes a relation on programs. And when that relation is very, very large, that means many programs are the same. And if many programs are the same, then that means that optimizers have more possibilities, more things that they can do. Meaning that there are a larger number of optimization opportunities that a compiler has available to it. And that's a desirable property. It also means that more programs are the same. So for instance, like, imagine that, let's say you are a professor and people were sending you homework assignments, and you wanted to know whether or not the program that they wrote meant the same thing as your version of the assignment, which you knew was correct. Well, then you could use an observational equivalence to determine whether or not they were exactly the same. Not exactly the same, but whether they did the same thing. So a way of verifying or checking observational equivalence would be a way of driving an optimizer, it'd be a way of driving a verifier. It's a very powerful theoretical tool. And we came about context because we were interested in factoring out our step function to make it simpler. All right. That's enough for today. This is a little bit of a shorter class. We'll come back in just a moment to do some more.